We're going to first talk about Newton's three laws, which will be covered in the reading due Monday as well, but we'll give you a brief overview of them. You probably already know them. Motion. I'm going to put them in order, although I don't expect you to remember them in a particular order. Number 2 you probably will, because I'll refer to it as Newton's second law so often. Anyone know any of these laws of motion?
An object of motion will stay in motion.
Yeah. And?
Unless the force is acted upon it.
Right. So I'm going to rewrite that just a little to add some more detail to it. An object at rest, we'll start with, will remain at rest.
Please say it's not.
And an object in motion will continue at a constant velocity. So that's important too. Unless acted on by an unbalanced outside force. Well, let's just say an unbalanced force. So if we stay at rest or continue at a constant velocity, what do we lack? You lack acceleration. So an object won't accelerate unless there's an unbalanced force. Newton's second law puts some math along with that. Does anyone remember the math formula that goes as one of these? No, that's
I know.
That's second semester. We already mentioned this one. And actually, this is that funny thing which...
What's that?
You guys know what that is? Sigma, which means what?
I can look at my notes right now from that.
Greek letter sigma, the capital S sound.
It's not fun.
No, friction is fun, but that's next week.
You guys are learning that in math?
No, I learned that last year.
This means sum. It's a Greek letter S, and it means sum. S-U-M. So it's the total forces acting on something are equal to the product of that object's mass and its acceleration. Then we get another law. You know this one too.
Is it the F equals M times G?
No, that's an example of this, because that F is gravity. Force of gravity is equal to mass times the acceleration of gravity. We just have a special notation for that acceleration. I will give you a hint.
I don't know. Horseman?
Yeah. You don't have the right to touch.
Something with an equal amount of force.
Yeah. So which law? You remember the wording now, Kevin? For every action, there is an equal and opposite reaction. which means if I push on you with a force, you push on me with the exact same force, just in the opposite direction. And that goes even if I'm throwing something. Clearly I'm applying a force to it. It's actually applying the same force to me. I don't move because I'm way bigger than this. But when you think of like a pitcher who has to really push off the pitcher's rubber to throw it that hard, if he was on flat ground, or she, it's much harder to get the ball going fast because you need that plant so that you don't move backwards. If you were on an ice rink, you couldn't throw it as hard because you'd slide backwards. Rockets work like this because they shoot exhaust out of the bottom and the rocket goes the other direction. So we see that all over the place. We are going to apply this in our first homework that I want to get a little bit of an intro to right now.
I guess it's Tuesday.
No, let's do one day along with the reading.
Yep. But tomorrow's a work day too. So this sheet is on the back of your calendar sheet. It goes over some of the rules and a couple of real simple practice problems for free body diagrams, which is a way to sketch out and then solve the result of forces acting on a body. So the first thing I want to talk about are the different types of forces. One important one is friction that we mentioned. You can think of forces, there are a couple definitions. One way to think of forces is that they are a push or a pull. Another way to think of them is that they are the agent that changes one type of energy into another. So if energy changes forms, there must be a force present somewhere in there. So friction is our first one. Think of friction. Friction is involved when two surfaces slide against each other, or when two are kept from sliding against each other.
I already looked at it. We both say 3.1.
Yeah, it's a long homework. It's a 3-page homework. So you should have one sheet on the back of your calendar, which is what we're talking about now, and then one full sheet front and back of some problems. So think of friction. What kind of energies are involved with friction? What kind of energy is it? Do you see me starting with? Kinetic friction, or kinetic energy of motion, right? So you've got two things moving, or one thing moving against the other. What kind of energy does friction change that into? Thermal. Changes it into heat. We note it in kind of a script way, so we got frictional force. When we're abbreviating it, we use a script F. And there are two types that we'll talk about. Kinetic, which is moving. When two things are sliding against each other, it's kinetic friction. When two things are held together and kept from sliding, it's called static, which is not moving or changing. So some examples, an example of that would be the stapler on this book. Not a very good example, it slides right off. Let's try tape, that'll work better. So static friction, there's no real static friction now because there's nothing that would make it go to the side. But as soon as I start tilting it, now gravity wants to pull it off the side. Static friction is keeping it from moving. If I go a little farther, then that static friction breaks down and it changes into kinetic. And we'll do an experiment on that. Another good example of where static is important is in like a wheel. So if you've got a tire here and it's rolling, well, it's not sliding against one surface against the other. It's rolling instead, one point going onto the other and gaining traction. That's another application of static friction. We don't want it to break traction because then we don't have very good control on cars. So think of driving in icy conditions. That's what anti-lock brakes are for, to keep it rolling rather than to keep it sliding. And we'll study more about why one is more beneficial than the other. But those are examples of each of those. We've got normal forces. Normal here is a math term. Normal in math means orthogonal, or in easier terms, perpendicular. So these are perpendicular forces between surfaces, touching surfaces. Whenever two things are touching each other, there is normal force. We abbreviate it as an Fn, and then we'll often have one or two things afterwards denoting it. We get a lot of these when we're writing things out, so we want to keep track of which one's which, and we'll talk about how to do that later. But we often have a little indicator of what they're applied to. But the Fn means normal force. Normal force, as you see between my hand and the book. What direction is my hand applying a normal force? Yeah, up, and the book applying a normal force on my hand, down, and they're equal and opposite. Even if I'm moving it up or down, they're equal and opposite. The force in between there, those are the same. Two normal forces here, four maybe, but both of my hands are applying normal forces in towards the book. The book is applying a normal force outwards towards each of my hands. What force is keeping this book from falling? Static friction. Right, so if I don't, we all know that too, if I don't push hard enough, there's not going to be enough friction and it'll just slide. So I have to apply enough force inward so that there's enough static friction to offset gravity. Next force, weight. Weight is an often misquoted one. Weight is just the force of gravity. It's always straight down towards the center of the earth. And this is the one where if we apply Newton's second law, we define it as, we can write it as F sub g if we want to, or we could write it a slightly longer way that tells us more information. It's the mass of an object times the acceleration of gravity. I'll usually write it like this when I'm drawing out images and things because it's the same number of letters and it gives more information. Okay, and of course g is 9.8 meters per second squared. We don't use the negative sign normally, even though it technically is there. We just say something is 500 newtons, not that its weight is negative 500 newtons. That part is implied. See, we've got, and then the last one we've got here is tension. Tension is pulling force. We abbreviate it usually with capital T. I think for the sake of our video especially, we'll stop it there.